test for that. And so it's not like I'm going to have a test for every single chapter. What I do is, for example, chapter 25, which is the nuclear chem, and chapter 24, part 2, is definitely on the final. But probably chapter 20 I'll have to include on the final as well. And so there'll be extra questions from those. But it's not too many extra questions because, except for chapter 20, I won't go in as much depth for some of the other stuff. Like chapter 25, what we do is, or what I do is just a brief survey of nuclear chem. And so for chapter 25, if you look at the homework assignment, it's very short, plus the material that's covered is just going to be from lecture. So just hit the main parts of nuclear chem. And so, yeah, we'll be able to finish the material. And so we have 19, which we're finishing today, and then I'll talk a little bit about 20. And then 24, the second part of 24, and then 25, nuclear chem. Nuclear chem I usually discuss in about 1 hour to 2 hours. And that's it. All right, let me talk about the last part of chapter 19 here. Get rid of this window. So we talked about corrosion, unwanted voltaic cells, and electrolysis, a little bit about electrolysis. We need to talk about is, let's see, stoichiometry, which isn't listed here, but it's fairly straightforward. Stoichiometry, we use the number of electrons transferred. And so use either the half reactions or net reaction. The half reactions are a little bit easier because you can see how many electrons are transferred directly. So for the net reaction, you have to determine how many electrons are transferred by using oxidation states. And coefficients to determine how many electrons. Transferred. And so if we look at zinc, zinc solids, probably one of the most common reducing agents in batteries. This forms Zn2 plus 2 electrons. It's not so expensive, meaning it's fairly common metal. And it's a good reducing agent. Its reduction potential is high or low. It's a good reducing agent. Well, this is kind of a trick question. It wouldn't be, if it's a reducing agent, it's not reduction potential. If it's a reducing agent, it should be the opposite, which would be, so its reduction potential is going to be very, very, very low, probably lower than anything on the table. But its oxidation potential should be high. And a reduction potential is going to form a zinc anion, like Zn minus or Zn2 minus, which is not going to be very favorable. Its oxidation potential is high. Over here, if we look at the net reaction, we have to balance things out. So let's take a look at a net reaction from the book where we have to determine the number of moles of electrons that were transferred. Let's see where was my book. So, for example, in the battery, the car or automobile battery, we could figure out this one homework problem, which asks you to determine the number of moles of electrons transferred in that particular cell. Well, let's see. Just try. This one here is pretty straightforward because this is a half reaction, number 57. And so we could easily see how many moles of electrons are transferred. How many moles of electrons? Well, we just read it like any other species here. 1 mole of manganese 4 oxide, 2 moles of water, 1 mole of electrons produces 1 mole of manganese 3 hydroxide plus a hydroxide ion. Is this a reduction potential or oxidation potential? This is a reduction potential. Is this reduction potential fairly high or kind of low? Or where would you place this reduction potential? In the middle. Good. This is in the middle. It's just a little bit weaker than what? Hydrogen ion, H plus. And in fact, this is the oxidizing agent in your battery, you know, your little batteries that you have. It's a pretty decent oxidizing agent, you know, but this would be it. This is the manganese 4 oxide, which is a solid in the paste. It's the thing with manganese 4 oxide is it's a fairly inexpensive oxidizer. And we see manganese 4 oxide in nature. It's this black coating. If you've been out to the desert, you look up at the cliffs and you can see this shiny black coating. That shiny black coating is called desert varnish. And this manganese 4 oxide is the desert varnish. So if you crush that up, you can make a battery out of that. Let's see the lead acid battery here. All right, I can't find it right now, but let's just use this one here. How many moles of electrons were transferred here? Now, permanganate is a much more powerful oxidizer than manganese 4 oxide. Manganese 4, the oxidation state is +4, but in permanganate, what's the oxidation state? Permanganate, +7. So here, it's not so obvious how many moles of electrons were transferred. So what we have to do is we just pick one. Like, say, for example, we pick permanganate. So permanganate went from +7 on the left to what on the right? +2. And so there's only one permanganate here. And so how many electrons were gained or lost? 5. 5 electrons gained or 5 electrons lost? Gained. So reduction is gained. So permanganate has a pretty high reduction potential. You know, one of the higher reduction potentials on the chart. Well, who did it take the electrons from? It took it from cerium. And so if we look at cerium, it's +3 to going to +4. So each cerium lost 1 electron, but we have 5 of them. And so 5 times 1 gives us 5. So those are 5 electrons lost from 5 ceriums. total. And so in this particular reaction, we have 5 moles of electrons transferred. Sometimes the reactions get a bit more complex, sometimes not. When we look at cell diagrams like this one, we don't have to have it balanced electronically. And so we just worry about the concentrations. And when we do the balancing, then we just balance it as we balance regular redox. That is, make sure the moles of electrons gained is equal to the moles of electrons lost. They have to match. Otherwise, we're going to have electrons left in the net reaction. In this particular case, chromium-3 goes to chromium-2, so that's 1 electron gained, and vanadium-3 goes to vanadium-2, that's 1 electron lost. So this is already balanced here in the cell potential here. Over here in this next reaction, we can see that we have copper-1 going to copper-2, so that's 1 electron lost. And we have 2 of them, so that's 2 electrons lost. And then tin-4 goes to tin-2, that's 2 electrons gained. So electrons balance here. For this reaction here, how many moles of electrons were transferred in this particular reaction for number 30? 2 is correct. Probably the easiest to look at cerium. Cerium goes from +3 to +4. For perbromate, it's a bit more work to figure out. All right, once we know how many moles of electrons, then stoichiometry for, I don't want that here. Stoichiometry, we have a number of different ways we can tackle the stoichiometry. Save this. It lets me save. When we do electrochemical stoichiometry, we need a couple of other things. We need the Faraday constant. And what was the Faraday constant? The Faraday constant was the ratio between what and what? It's the ratio between coulombs, 96,485 coulombs per mole of electrons. A mole of electrons would be an Avogadro's number's worth of electrons. And so we need the charge for certain things like coulomb. You know what a coulomb times a volt is equal to? I mentioned this briefly before, but I don't know if you caught it or not. Coulomb times a volt? Joule, right. And so sometimes we'll need coulombs for that. Sometimes we're calculating volts. Coulomb times a volt is a joule. It's the amount of charge that we move through the circuit. And we need one more thing. We need something called amps or amperes. And 1 amp is defined as 1 coulomb per second. 1 coulomb's worth of charge per second. So if I had 1 coulomb's worth of charge, how many electrons is that? Well, we could use the Faraday constant to figure out how many electrons were transferred in a second. And so 1 coulomb per second. Usually with batteries, we're looking at, it depends on the battery. An automobile battery can draw like 30 amps, of charge in 1 second. 30 amps, that's a lot of electrons there. And that can be quite dangerous to have that many electrons be transferred. A lot of other applications we're looking at very small, like 1 amp or less of charge. So household, household outlet has a breaker, and the breaker is set at 15 amps usually. And so if it goes more than 15 amps, then it shuts off the circuit. But some breakers you'll need more. If you get an electric vehicle, you'll need a 50. Well, 50 is on the low side. They want more like a 60 amp breaker. You know, that way you can get enough electrons to flow. Otherwise, it takes a long time to charge. If you try to charge a car with a household outlet, you're looking at a few days to charge it to 100%. And so I have a 50 amp breaker. But for us, that meant having to sacrifice something, sacrifice electric dryer, so a gas dryer. Otherwise, didn't have enough current in the house. Most places will have a limit, and if you need to go over that limit, you have to have it wired from the street. And having it wired from the street can get very expensive, so there's got to be a lot of infrastructure change. But we're all interested in amps. How many total amps is your box? Like industrial, 400 amps. Industrial house. How many total amps do you have? That's going to dictate what you can power. And so we can measure amps easily. We have something called an ammeter. And so there are two things we measure in a battery. We measure volts using a voltmeter and amps using an ammeter. Amps just measures the flow, and it measures the flow in coulombs per second or amps. So this goes for both voltaic and electrolytic cells. We can figure out the stoichiometry. We just measure the amps. Cells here. All right, so let's take a look at a stoichiometry problem, and it's pretty straightforward, the stoichiometry. Most people don't find it very difficult to do. A lot of the applications are towards electrolytic, but you could do it for voltaic just the same. It's just the exact same stoichiometry. One's spontaneous, the other you have to use a power supply. So let's take a look at this. All right, let's look at number 70 here. Let me copy this. All right, calculate the quantity indicated for each of the following electrolyses. A, copper 2 plus remaining in 425 milliliters of solution that was originally at 0.366 molar copper 2 sulfate after passage of 2.68 amps for 282 seconds and the deposition of copper at the cathode. So here it's a bit easier because all we need is a half reaction. So we're going copper 2 plus 2 electrons. That's going to yield copper solid deposited at the electrode. Now, the book has a weird thing about naming the electrodes, but this is fine because it's always the same, whether it's an electrolytic cell or a voltaic cell. What happens at the anode? Oxidation or reduction at the anode? Reduction? It goes alphabetical. So, oxidation. At the anode's oxidation, at the cathode is reduction. Yeah. Now, it gets tricky because in an electrolytic cell, you have to have another power source or another battery in between the original. And so sometimes the book will label, because the cathode of the power source goes to the anode of the electrolytic cell. So sometimes they'll just label it, well, the cathode, because you attach the red wire to it. And so, so some people get it mixed up, so be careful with that. So you'll see it in two ways. All right, so this is just stoichiometry. So we just use the dimensional analysis for this. So we start off with a fixed 282 seconds, and then just look for conversion factors. And we got 2.68 amps, so that's 2.68 coulombs per second. And so the seconds cancel. And then we have Faraday's constant, which we use a lot in this, from 96,485 coulombs per mole of electrons. And then we have the half reaction here, that is, 1 mole of copper 2 plus per 2 moles of electrons. So the coulombs cancel, the moles of electrons cancel, and that leaves us with moles of copper 2 plus. Well, this is the moles of copper 2 plus reacted. And then we just, if we want the moles of copper 2 plus that remains, then we just do a little bit of subtraction here. And so moles of copper 2 plus that remains is equal to the initial minus the moles of copper 2 plus reacted or consumed. And then we could figure it out. So the stoichiometry, we just need amps. We need time. Time is a fixed quantity. And we need Faraday's constant. B, calculate the time. Let's see. This is going to crash. You have too much stuff open. Yeah, I upgraded the RAM on this computer. This originally came with 8 gigabytes, so I have 16. Still not enough. So time required to reduce silver. So this is just dimensional analysis once again. So in 255,
It was the moles of copper 2 plus that remain equals the initial minus what?
the moles of copper 2 plus reacted or consumed, which is what we just calculated in that previous dimensional analysis. And then if they're asking for the concentration, then we just take the moles divided by the liters of solution. You get the concentration.
How do we know this is a reduction, like half reaction or an oxidation half reaction?
Okay, how do we know it's a reduction half reaction? Because number one, it's probably the biggest thing is it's saying deposition of copper here. So what they're meaning is copper is the product. And so if copper is a product, then copper 2 must have been the reactant. And that's pretty much what clued me in. It's the copper that was deposited. Number 2 is just from experience, copper plating is very commonly done, but it doesn't have to be. It could have been the oxidation, in an electrolysis cell. It would have been fine too, but it's just copper 2 Yeah. The other clue would be remaining. If it were oxidation, it would say copper 2 produced, or what's a new copper 2 concentration, something like that. But we know the copper is being produced at the cathode. Cathodes where reduction occurs, so that's where I got it. It takes a while for all these to click, oxidation potential, reduction potential, and get a feeling for what they mean. But eventually it just clicks, and then it's not that big of a deal anymore. But initially it's really confusing. The time required to reduce silver ion. So I already know we're reducing silver ion. So silver ion plus an electron. Reduction is gain, Rig. This is going to silver metal. So this is the reaction here. And so we want the time required in 255 milliliters of silver nitrate from 0.196 molar to 0.175 molar by electrolyzing the solution between platinum electrodes with a current of 1.84 amps. So what our given here is, the amps is just a ratio. It's an intensive property. 255 milliliters, that's an extensive property. So that's what we start with here. Molarity is just intensive property. So in dimensional analysis, we start with a fixed, which is this extensive property, 255 milliliters. And then we're going to convert that to liters. Okay, but where do we go from here? So from here, you can see that the concentration dropped. And from that concentration drop, we could figure out, how many moles. So we could calculate the moles of silver ion present at 0.196, and then calculate the moles present at 0.175 and subtract the two. That's option 1. Option 2 would be a little bit quicker. We can just calculate the delta moles, delta molarity, delta moles per liter. Let's just do. So here, going from 0.196 to 0.175, let's just do that here. 0.196 minus 0.175. 0.021 molar. So that's how many moles per liter we lost. So I'm just going to use that over here, 0.021 moles of silver ion per liter lost. This is silver ion lost. Okay, if I have that many moles of silver ion lost, and I see it's a 1-to-1 mole ratio with electrons. So 1 mole of electrons per 1 mole of silver ions. And then I can use the Faraday constant, which is 96,485 coulombs per mole of electrons. And then I can use amps, because amps is coulombs per second, so that's going to be 1 second is equivalent to 1.84 coulombs. And then I might change the time unit, or I might leave it as seconds. And so let's go ahead and calculate this. It's going to be 255 divided by 1,000 times 0.021 times 96,485 divided by 1.84. 280 seconds. 280.8 seconds. We're allowed to, it looks like 2 sig figs, so we'll just say 280 seconds. So these are examples where all we had to use was the half reactions, not the full balanced reaction. Sometimes we'll have to use the full balanced reaction in other stoichiometry problems. But whether it's a voltaic or galvanic cell, it's the same procedure. Okay, let's take a look at an example of a Nernst. That is, here's a voltaic cell. Um, Here in 48. Here we have a silver anode or silver cathode. Anode. This is why we it doesn't really matter. Does the oxidation occur in the left beaker or the right beaker? It doesn't matter. It depends on where you're standing, right? But when we write it down on paper, we always try to do it the same way each time. Unless if it's a electrolytic cell, then I try to reverse it. That is, I have the electrons flow not left to right, but the electrons flow right to left. You know, just to keep it in mind. So electrons are flowing left to right. Anode over here. What's the cathode made out of? The cathode, job of the cathode has two purposes potentially. One, it could be a reactant, or two, it could be both, or actually three. It could be both reactant and a passageway for the electrons. We have to have something to feed the electrons over there, and so the cathode. Like, for example, if we look at this anode here, the anode serves dual purpose. This anode over here is a reactant. Silver gets oxidized, and it also transports the electrons. Over here, iron 3, yes, you might say iron 3 is the cathode. No, iron 3 is the oxidizer, but the problem with iron 3 is who does it give the electrons to? It's got to give the electrons to the electrode. And so the electrode is way out here on the right, and that's platinum. And so iron 3 is going to give the electron. Actually, it doesn't give electrons. It takes electrons. Who's it taking it from? The iron 3 is actually taking the electrons from platinum, but platinum is not going to lose them because platinum is going to have a wire connecting it to silver. And so the iron 3 is actually oxidizing the silver. Does that make sense?
Is the actual anode and cathode always going to be at the end?
Yes. It's always at the end. So let's look at number 50 here. Do you see what's the anode made out of? And the cathode? Yeah, exactly. And so it's always at the ends. Let's see if we have another one. No, I don't. Now, the weird thing is, when we do our predictions for redox, like we're going from stronger oxidizer to weaker oxidizer, we're assuming standard conditions. So when we predict a redox reaction using the chart, everything has to be under standard conditions. If they aren't under standard conditions, then our prediction might be wrong. So normally when we think of what's a stronger oxidizer, iron 3 or silver ions, you might go iron 3 is a stronger oxidizer. Well, that's under standard conditions. If you're under non-standard conditions, we could have it flipped. That is, we also have to pay attention to not just the strength, but also what? The molarity or the concentration, the strength in numbers. So you could have a weaker oxidizer oxidize a stronger, if the numbers are mismatched. So what is E the cell initially? So what we have to do is we have to look at under standard conditions, what is E the cell for the, I just forgot. So we need to calculate the E naught of the cell for this, that is, under standard conditions. And so we look for silver goes to silver plus, and then iron 3 goes to iron 2 plus, and look at those. And so we look at the anode, which is the oxidation potential. And the easiest way, if you get confused, is just do this. It's the oxidation potential, plus the reduction potential. The reduction potential is just iron 3 goes to iron 2. Now, when we draw a vertical bar, if the phase is different, but iron 2 and iron 3 are in the same solution. They're in the same phase. And so if they're in the same phase, we use a comma. And so this is iron 3 goes to iron 2 in the same phase. We use a bar here because silver is a solid, silver ion's aqueous. And so we just look at the anode potential and combine it with the cathode potential, or we look at the oxidation potential and combine it with the reduction potential here. And so we go to the chart and take a look at the chart for these potentials here. And the chart, you could use Appendix D. Appendix D is a bit long, so I'm just going to use the Chapter 19 chart here. So we're looking at silver goes to silver ion. I would think that has a fairly low oxidation potential or fairly high oxidation potential. What would you say initially? Silver goes to silver ion. Low oxidation potential or high oxidation potential? In other words, what I'm asking you is it easy to oxidize silver or is it hard to oxidize silver? Silver is a coinage metal. Well, easy relative to what? Easy relative to zinc? Easy. Should they make coins out of zinc rather than make coins out of silver? No, you could make coins out of copper, but copper pennies eventually they kind of discolor. Whereas silver, if you have a silver quarter from the 60s or something like that, it still looks pretty good. But if you have a copper penny from the 60s, it's probably going to look black. This is oxidation. Yeah, silver tarnishes. In fact, that's one. Let's just take a look at that since we're on that topic. So if you have like old silverware, you have to worry about silver tarnishing. That is, it gets a black coating on it. This is actually a homework problem. But it's being oxidized. Silver tarnishes silver sulfide. And there's a little bit of like hydrogen sulfide in the air. And there's some weird redox reaction that happens. This happens with copper too. You see the green coating on copper, like copper roofs have that green coating. That's from sulfur in the air, usually in the form of hydrogen sulfide. There's small concentrations, but it causes that. So the silverware turns black eventually over time. What a lot of people do is they use polishing compound. Now, the problem with the polishing compound is you're removing the silver sulfide. If you're removing the silver sulfide, you're losing silver. And so you're going to have fewer grams of silver than you started with. And so what people don't want to lose any silver because silver is expensive. And so what they want to do is they want to reverse it. Well, fortunately, this reaction is reversible. And so what you can do is you can convert the silver tarnish back into silver metal without losing any. But if you look at the potential there. Is that a high potential or a low reduction? This is a reduction potential. This is a low reduction potential. which means it's not easy, right, to reduce. It's hard to, it's not a very good oxidizing agent, this is. And so we need a good reducing agent. We need a good reducing agent with a high reduction potential. What should that reduction potential be? We need a reducing agent with a reduction potential greater than what? Yeah, 0.691 volts. Any reducing agent greater than 0.691 volts should work. And we need something that's not too hazardous and that's cheap. And so do you know what people use? So a tarnished silver spoon is placed in contact with a commercially available metallic product in a glass baking dish. So the glass is not used, but the metal, we want some metal with a oxidation potential greater than 0.691 volts. Boiling water to which some sodium bicarbonate has been added. Sodium bicarbonate is like the salt bridge, right? It's poured into a dish and the product and spoon are completely covered. Within a short time, the removal of tarnish from the spoon begins. What metal or metals are in the product? What is the probable reaction that occurs? What do you suppose is the function of sodium bicarbonate? An advertisement for the product appears to make two claims. One, no chemicals are involved, and two, the product will never need to be replaced. How valid are these claims? I'm a bit confused about the metallic product. The metallic product is not the product of the reaction. It's the metal reactant that they're selling as a product. And so, well, this metal, whatever that metal is, it should have a oxidation potential greater than 0.691 volts. So let's take a look and see what metal. You probably can guess what the metal is. So let's try to guess what the metal is. And so we're looking at a oxidation potential. This is a chart of what? Oxidation potentials or a chart of reduction potentials? Reduction. So we have to reverse it. I've got to change the sign. And so the highest oxidation potential is lithium at plus 3 volts. So obviously they aren't going to use lithium because lithium will react violently with water. Potassium, 2. Calcium, sodium. Sodium, calcium, potassium, lithium, these all react violently with water. Magnesium, have you ever seen magnesium catch on fire? It gives a very intense bright white flame. If you haven't seen it, I'll do it as a demo. It's probably what? Will zinc work? Well, zinc, it would be plus 0.763 volts. How many volts did we need? Plus. Yeah, zinc would work. But what's the problem with zinc? Maybe zinc is too good, not stable enough. So zinc's going to undergo oxidation. All these metals undergo oxidation. How about iron? Iron, is that enough? No, but iron's a problem because it's going to rust in the box. And if it rusts in the box, it's no good. Zinc is even easier to oxidize than iron. And so zinc is going to oxidize. But aluminum is easy to oxidize. The difference between iron and zinc oxidation is the structure, the lattice structure of the oxide that forms. Iron oxide is very porous. And so the underlying iron can easily be oxidized further, and eventually all the iron will be eaten away. Whereas aluminum, it forms a very non-porous oxide. That is, it forms an impermeable layer of oxide on the surface. So aluminum is kind of weird because what happens with aluminum, and this aluminum here, is just the surface gets oxidized, but it doesn't continue to become oxidized because it forms such a nice impermeable oxide coating on the surface, and so it protects it. But if you need to get it to react, well, you have to remember there's an oxide coating on the surface which can hinder reaction of the underlying aluminum, and the oxide coating is very tough, and so sometimes it's difficult to get it to react. But what do you think that block is made out of? Aluminum. And so they just put it in here. So this block is made out of aluminum, and then aluminum should have the oxidation potential to make this favorable, a positive E naught of the cell. So what metal or metals are in the product? Aluminum. What is the probable reaction that occurs? Aluminum goes to aluminum 3 plus, and then we have this, and then we got to balance it. What do you suppose is the function of sodium bicarbonate? Salt bridge. Otherwise, it's going to be slow. No chemicals are involved. Everything involves chemicals, unless you're in a vacuum. If you're in a vacuum, then there are no chemicals. And the vacuum has to be a perfect vacuum. And so they should say maybe no hazardous chemicals are involved. Those are household, generally regarded as safe. Grass, generally regarded as safe. Zinc is not safe. Little kids eat zinc or get zinc poisoning from eating pennies. Pennies with little nicks in there. The copper is okay, but the zinc inside is bad. To a chemist, everything's a chemical. But to most people, chemical means something bad. And so something bad would be something not something bad would be something that has some toxicity to it. So this is a way to, rather than polishing it, and removing the tarnish, it's better to reverse this reaction and keep all the silver. So I need to grab the potential. So silver goes to silver iron 3 goes to iron 2. So we'll just go to the chart and grab the potentials here. Silver, to answer the question, silver has a low oxidation potential. Low oxidation potential is minus 0.8 volts. It's hard to oxidize silver. This is why they use silver in silverware, although it tarnishes. Some people actually don't use silver because silver's not fine enough. If you have the money, what would be better than silverware? Platinum or gold. And so some people have gold spoons and gold forks, that kind of stuff. Other places they have silverware, like the Bellagio in Las Vegas. If you eat at the little restaurant there, they have silver, but it's silver coated. It's actually silver coated lead. Lead to give it some weight, so it feels like silver. But if they use solid silver, it'd be too expensive. So I think it's silver plated lead. Interestingly enough, I'm not 100% on that. Could be silver plated steel, but then it'd feel like a regular fork or spoon without the weight.
Is silver like a strong metal? Like it's not like super soft.
It's soft. Silver is kind of like gold and platinum. It's a fairly malleable, ductile metal.
So they put lead under the soft metal.
Yeah, but lead is also pretty soft as well, pretty ductile. But yeah, it's hard enough to hold its form. I mean, gold. If you have a solid piece of gold, it doesn't feel so soft. But
I was just thinking, like, if your teeth scrape it or something, you're gonna get lead.
Yeah. If the silver coating has a nick in it or something, then you don't want to swallow it. I'm not sure. I'm not 100%. Maybe they don't use lead. But I had read that somewhere that a lot of the silver plated. Let's see. No. Silver plated flatware. secondary images. Oh, okay, I'm wrong. That must have just been one of those urban myths that I bought into. This seems much more reasonable. Copper or brass. But you have to worry about brass. Only certain brasses are allowed in plumbing. You know, if you go to Home Depot or someplace like that and you're buying a brass fitting, there are two types of brass fittings. There's brass fittings for gas lines. The brass fittings for gas lines contain lead. And then there's brass fittings for water lines. Gas fittings for potable water lines are not supposed to contain lead, but they're easy to get mixed up. And so you have to be careful which brass fittings you use for water. Usually they have something called NSF. NSF has two meanings. NSF means National Science Foundation, and NSF means National Sanitation Foundation. The National Sanitation Foundation keeps track of this type of stuff. So if they use lead underneath there, it would not be NSF approved. But brass. Copper is only 9 grams per milliliter. 8 or 9, 8.9. Lead is 13 for the density. So it depends on how close you want the density to match. All right, so minus 0.8 volts, fairly low oxidation potential, hard to oxidize. Aluminum, 3 plus reduction potential, or no, what was it? Iron 3. Iron 3's reduction potential should be fairly high. If you look at iron 3's reduction potential, it's 0.771 volts positive. And so it's a decent oxidizer. Iron 3 is a better oxidizer than oxygen. Well, this oxygen, there's another oxygen up here. So let's say iron 3 is better oxidizer than iodine and copper 2. But it's a worse oxidizer than silver ion. Well, if it's the worst oxidizer than silver, is it going to work? So let's take a look. It's not going to work. Under standard conditions, this is not going to work. Because silver is minus 0.800 volts, and iron 3 is plus 0.771. 0.771 volts. And so this is going to give us minus 0.029 volts. This is non-spontaneous under standard conditions. However, it's not just the strength, it's also the number. The number is going to be related to the concentration. And so we can see if this cell is going to run spontaneously based on this. And so under non-standard conditions, we might actually get a positive voltage rather than a negative voltage here. And so E of the cell is equal to E naught of the cell. Now, you know, all the thermodynamic stuff gets all mixed up. Is it plus or minus? Well, you know, sometimes it's plus, sometimes it's minus. In this case, it's minus 0.0592 volts over Z. Z is also N, log base 10 of the product concentrations over the reactant concentrations. And so we need the net reaction here. And so the anode half reaction is silver solid goes, should be no sign. Silver solid goes to silver ions plus an electron. And then the cathode half reaction is iron 3 go plus an electron goes to iron 2. So it's one electron. So this just is simple, 1 to 1. Silver plus iron 3 goes to silver ion plus iron 2. This reaction is non-spontaneous because we're going from weaker reducer oxidizer to stronger oxidizer reducer. So under standard conditions, it's non-spontaneous, but we don't have to do everything under standard conditions. We can go non-standard, and that could change the driving force, which it does. So this is going to be the log of the Q, which is the products over the reactants. Silver is a solid, so that gets left out. So this is just iron 3 plus here. And so we just plug in the concentration. Silver ion concentration, 0.015. Iron 2 concentration, 0.045. Iron 3 concentration, 0.055. Z is how many moles of electrons were transferred in the balanced chemical reaction. Here, we have to use the net reaction. We can't use the half reaction for this. It has to be the net. And so how many moles of electrons? Z is equal to 1. 1 mole of electrons. Units will cancel here. And so this is going to be strength in numbers. So let's go ahead and I'm going to calculate it here. That is 0.015 times 0.045 divided by 0.055. So the more reactants we have, the bigger the denominator, the more positive this will become. Take the log of this. Times 0.0592 negative divided by 1 is the same thing. And then we calculate E naught of the cell as 0.029 negative, so minus 0.029. And I get 0.084 positive. So just because the reaction is non-spontaneous, we can change things. You know, we can change things like the concentration. That's non-standard. What else can we change? Pressures. What else can we change? We can change temperatures. You know, we can try to change things to make a non-spontaneous go spontaneously. Here they just change the concentrations. We can make this. And in fact, the more, the higher the concentration of the iron 3, the higher the concentration of the oxidizing agent here, the more favorable this will become. So rather than 0.055, we want 1 molar. What should happen to the voltage? We can't change the concentration of silver metal because that has a fixed concentration. It's pure, 100%. So E of the cell initially is 0.0841 volts. As the cell operates, will E of the cell increase, decrease, or remain constant with time? It's always going to decrease, right? Unless it's all solids and liquids. Then it stays constant. The ratio is going to change. What will E of the cell be when silver ion concentration has increased to 0.020 molar? So what I do here is I just set up a ice table. And we're taking snapshots of the reaction as it occurs. So initially we're starting off with silver is pure. So iron is 0.055. The silver was what, 0.015 and 0.045. And then there's a change, and then we're going to stop. This is some point in time, T1, we'll call it, or T2, T final. This doesn't mean the reaction's ending here. It just means we're stopping. we're stopping when the silver ion concentration has grown to 0.020. So we went from 15 to 20. And so we're going to use this table to figure out the rest of it. And so this is going to be minus x plus x plus x. And so what is x? .005. And then we just use the Nernst equation again to calculate E of the cell. This is going to be log of 0.02 times 0.05 divided by 0.05. The 0.05s will cancel. It's just log of 0.02. Calculate that. What will be the silver ion concentration when E the cell is equal to 0.010 volts? Okay, when E of the cell is equal to 0.010 volts, this is equal to E naught of the cell minus 0.0592 volts times the log of the ratio. So we could figure out what the ratio is here. And so E naught of the cell was 0.029 negative. So I'm going to add 0.029 volts to both sides. So I'm going to get 0.039 volts is equal to negative 0.0592 volts log of the ratio. So I'm going to divide that 0.039 divided by negative 0.0592. Oops. 0.039 divided by 0.0592 negative. And then I'm going to take the anti-log of that. And so I get a ratio. The ratio is equal to 0.2193 here. So we have this situation where I'm going to work backwards from the ice table. So this has to be the ratio at T final. And so what we're going to do is we'll just set up the ice table again. Silver solid plus iron 3 plus goes to silver ion plus iron 2 plus. I'll call this T final here rather than equilibrium. It's not the equilibrium. The battery's still alive. It's not dead. And so the initial was 0.055. The silver was 0.015. This is 0.045. That was the case. Yeah. This is going to be minus x plus x plus x. So we're going to have 0.055 minus x, 0.015 plus x, 0.045 plus x. Then we just have to figure out what x is. And so this is like an equilibrium calculation. 0.015 plus x times 0.045 plus x divided by 0.055 minus x is equal to this ratio that we just calculated, 0.2193. 0.2193. And then we solve for x. And once we solve for x, we can figure out what the silver ion concentration is. What are the ion concentrations when E of the cell is equal to 0? So we're going to let this cell react completely to 0 volts. And so we need to figure out what the ion concentrations are. So that's equal to E naught of the cell minus 0.0592 volts log divided by Z, which is 1, log of the concentrations. What do you think they are? In other words, do you think that, let me ask you this. When this cell goes to 0 volts, will the iron 3 go to 0 molar? That is, we completely consume all the iron, because the iron 3 is going to be the limiting reagent. We have infinite solid here, so we just have to make sure we have enough solid. Infinite solid doesn't mean we need to buy infinite pounds of silver. It just means it's excess reagent. Yeah, so you're right. It doesn't go to 0. It doesn't have to go to 0 to go to 0 volts. And there's going to be a little bit of iron 3 left over to maintain equilibrium, the tie. So add 0.0592 to both sides. And then take the anti-log of that and to get the ratio. So we'll just do that in the next step. 0.029 plus 0.0592. Take the anti-log. .225. And then we do the same thing. 0.015 plus x. 0.045 plus x. 0.055 minus x. This will cause it to go to 0 volts. And so just solve for x. We'll have to do quadratic here to solve for x. But that's the basic. I mean, this is like a K calculation. So, anyways, when E of the cell goes to 0, what is delta G equal to? Yeah. When E, because delta G is minus NFE, or Z, minus ZFE. And so when E of the cell goes to 0, delta G is also 0. And we've done delta G equals 0 calculations, many of them, right? Before. And we can make delta G go to 0 by changing the temperature. We can make delta G go to 0 by changing the concentrations, changing the pressures, just go non-standard. Well, the same thing with E of the cell. These are all very similar. Except the sign's flipped, you know. Delta G, it's plus RT, L, and a Q. In the Nernst, it's minus because delta G you want negative for spontaneous. E of the cell you want positive for spontaneous. So the sign's going to be flipped for this. All right, so those are some applications of redox chemistry. And the Appendix D table with delta H, you know, of formation, delta G of formation, and the absolute entropy is S. The other way of getting all those thermodynamic calculations done is by E calculations, because we can relate E back to delta G, and then we can do all those calculations there. So, although it doesn't seem like they're connected, the E table, that chapter 19, the redox chart, is very useful for doing thermodynamic calculations as well. In fact, that's what we're doing. We're doing thermodynamic calculations here, and that's the driving force. Now, even though there's a driving force, the reaction could happen very slow. This is why, in the absence of, we don't absolutely need the salt bridge, as long as there's water present. The cations are eventually going to migrate to the cathode, and the anions are eventually going to migrate to the anode, but it's very slow. This is why, if they sold that product, think about if they sold the product, the silver, I don't know what they call it, but the silver tarnish converter, without the sodium bicarbonate, how many returns would they get? Everybody would return it because it's just not working. Well, it is working. It's just working extremely slow. You can't even see it happening because it's so slow, because the diffusion processes are so slow. So even though there's a driving force, we calculated this driving force is positive voltage. Not much, but enough. The greater the voltage, the faster it should probably happen. But it's not always the case. And so they would have gotten a lot of returns. If you don't use enough sodium bicarbonate, it's going to happen slowly. And so when we're thinking about chemical reactions and predicting chemical reactions, we need to think about the thermodynamics, the driving force, but we also have to think about the speed, the kinetics. Because whether you have a salt bridge there or not, did it change E of the cell? And does the identity of the salt bridge change E of the cell? What kind of salt you use? No, it doesn't. That is more towards the kinetics. So if we want to understand reactions thoroughly, we need to understand both the thermodynamics, the driving force, and the kinetics, the speed of the reaction. When we do our predictions for chemical reactions, we only looked at the thermodynamics. We didn't look at the kinetics. But in general, it can be said that if there's a high thermodynamic driving force, then those reactions tend to happen quickly and violently. But not always. Let's see if it'll save it now. Yes. All right, so this brings us to chapter 20, which is kinetics. We're going to do two approaches to our study of kinetics. One is strictly empirical. Have we graphed our kinetics data? I don't think so. So empirical means this. We want to predict, like, for example, we want to make predictions. Like, how fast is that reaction? How long do I have to wait? I don't have a lot of time. I need to make sure that that reaction happens within a certain amount of time, right? Well, how do you predict that? Let's say, okay, I'm curious, how fast this reaction is going to take. So can you tell me how many hours I have to wait, or how many minutes? How long is it going to take? Tell me how long. How long do I have to wait? I want to know. How are you going to predict that? Well, initially, what we're going to do is we're just going to predict it empirically, which means what? Yeah, empirical is based on observation. So you do it and see how long. And then after you see how long it takes, you can make a prediction. Well, it took this long last time, so it should take this long this time, Empirical, purely empirical. And so the first half of this book, I mean, this chapter, not the book, but this chapter is empirical. And so we're going to see, like crystal violet, how long did it take to decompose? And so when we look at it empirically, we like to graph it like, let's say, the concentration versus time, the concentration of the reactant versus time. How fast does that, in other words, does it happen linearly like this? If it happens linearly, we don't have to watch the whole thing. Maybe we watch the first couple of minutes. Let's say the first couple of minutes took this long, so I figure it's going to take another 60 minutes, something like that. And that's easy to predict. If it decomposes linearly, then you can extrapolate that out, right? And figure out how long that's going to take. But what if it doesn't decompose? What if it looks linear initially, and then all of a sudden it slows down? Like, whoa, it starts off like this and then slows down. Or actually, or what happens if it speeds up? I mean, right at the beginning it's so fast, but at the end it's super slow. So it's going so fast here, you predict it's going to end here in this much time, but in reality it takes this much time, whereas if it just decomposed linearly, it would have been way faster. Although it goes slower initially. And so we want to see the pattern, because based on the pattern we can make predictions, right? These patterns. And then if these patterns are consistent, then maybe we could call these laws, And that's as far as we get. Because in the scientific method, the scientific method does what? If we go back to the scientific method, what does the scientific method start off with? Observations. And then we look for what? Patterns. And if these patterns are consistent, we call them laws. And what are laws? Laws are mathematical equations that define the pattern. So you know the law of a straight line? What is the law of a straight line? Y equals mx plus b. That's the law of a straight line. What is the law of an exponential decay? Like this. We'll figure out the math for that. What is the law of this decay? We'll figure out. It's just a mathematical equation. Those are the laws. From the laws, we start to think, why do some things decay linearly like this and other things decay exponentially and different kinds of nonlinear patterns? What makes some things linear and some things nonlinear, and there are different ways that they're nonlinear. We have to come up with a what? Hypothesis. Hypothesis is trying to understand more fundamentally, what about the structure, what about the composition, what about the reaction that causes it to react this way or behave this way. And then from hypothesis, we go to theory. And so the second approach that we're going to take is a more theoretical approach. We're going to look at the theory of kinetics. And the theory of kinetics is going to dig deeper into what causes it to behave that way. And what causes it to behave that way is something called the mechanism. The mechanism is the mechanics of the reaction. What happens when it reacts? What electrons are transferred, what electrons are moved, what bonds are broken. the mechanism of the reaction details out structurally what's going on in terms of bonds and electrons and why it behaves this way. Mechanism, collisions and bonds and whatnot. And therefore, if we know the mechanism, if we know the mechanism of the reaction, we can predict, because theories should be able to do two things. What should the theories be able to do? Yeah, predict the future and also explain the current and past. And so theory should allow us to predict the kinetics, the empirical observations of the kinetics and elsewhere. And likewise, the empirical nature of the decomposition should give us insight into the mechanism. And so when we see how something decays, we get a window into its mechanism. How else are you going to see how things react? Can you watch them react? Like, for example, a methane and an oxygen. Can you watch it react? No, I mean, if you watch it, and in fact, well, actually, let me take that back, because the Nobel Prize in Physics. You know what the Nobel Prize in Physics was this year? The Nobel Prize in Physics this year was some insanely fast laser. Insanely fast in the pulses it gives off. I forgot how fast. Let me see how fast that was. They don't say how fast it was here. A tiny hummingbird can beat its wing 80 times per second. We are only able to perceive this as a whirring sound and blurred movement. For the human senses, rapid movements blur together. Okay, fine. But if you have a high-speed camera, it's fine. Atoms' natural timescale is incredibly short. In a molecule, atoms can move and turn in millionths of a billionth of a second, femtoseconds. These movements can be studied with the very shortest pulses that can be produced with the laser. Oh, here it is. Attosecond. Femtosecond lasers have been around for a long time, but femtosecond lasers are too slow. If you need a high-speed camera, you got to figure out what shutter speed you need to capture the hummingbird's wing. But you have a camera that's fast enough, and so technology just build faster and faster cameras with faster and faster shutter speeds. Well, this is a faster and faster shutter speed because these reactions are like hummingbird wings. You have to be quick in order to watch them. And so I was saying, can you watch the reactions? Well, now it's a lot easier to watch because they made an attosecond laser. In a femtosecond laser, can you count to 1 trillion in 1 second? That's how fast it is. It gives 1 trillion pulses in 1 second. That's like counting to 1 trillion in 1 second. It's just like mind-boggling to think about. But an attosecond is counting to a billion billion. Could you count to a billion billion in 1 second? That's how many pulses. In 1 second, you have not 2 billion, a billion billion, which is way, way more than 2 billion. And so it'd be 10 to the 18. 10 to 18 pulses per second. That's ridiculous. And so there you can maybe watch the reactions occur in real time. That would be pretty phenomenal. And so this is why they won the Nobel Prize, is because you can watch reactions happen in real time. It's amazing how they do it, these overtones. Constructive and destructive interference generates these pulses. It's pretty interesting. And then you can see, electrons move. that time. Usually things that happen way too fast to see. But anyway, this happens very slow usually, this kinetics, and that gives us insight into the mechanism, and we can hypothesize different mechanisms that can occur. And so the study of kinetics, people want to study how it behaves so that they get insight into the mechanism, how things react. Not only that, empirical is fine. We can stop at empirical because we might predict how long does it take milk to spoil. Should you wait? Okay, I'm going to wait 30 days. Some people don't want to wait. Some people don't have that patience. So what they want to do is they want to see how it decays initially and then extrapolate it out. And so like food, if you want to get shelf life of the food, they don't throw the food in there and then wait years. They just heat it up and then see and then make some calculations. And this would be what it translates to at room temperature. That kind of deal. So the first part of this here is we're going to do this. We're going to plot our data here and then just try to fit it to a mathematical function. Okay. And that would be the law. The law would be the mathematical function that this fits to. Okay. All right, so we're going to go to the computer lab. And like I said, I have to end early today. So what we'll do is we'll just go to the computer lab and then you can graph this data here and then work on your other labs. Have you guys identified your unknown acid? The unknown acid is going to be one in the list of acids that is on the handout. So it's not a terribly large list, so they limited it to. So take a look at the handout. If you don't have your handout, I'll put it up here. But you're going to have to identify your unknown acid, and you'll have to make some arguments why you think that's your acid. In other words, what evidence did you use to determine that? You can use multiple evidence, but not all of them should be weighed the same necessarily. Things like molar mass, we can calculate the molar mass because that's like a Chem 1A style calculation, but there's more evidence that we can get. These are the potential unknown acids. However, this is tricky because some people's acid matches acetic quite nicely, but there's one major problem with acetic acid, and that is acetic acid in pure form, which is sometimes called glacial acetic acid, is a liquid. Was your unknown acid a liquid? No. And so some people accidentally select acetic acid thinking their unknown was acetic acid because either the molar mass or the pKa matched very well, or maybe both of them match very well, but it couldn't be. So you want to use certain things. Was your unknown a white solid? Are any of these colored? So we can use multiple observations to try to nail down what our unknown is. Was our unknown easy to dissolve or hard to dissolve? That's trickier because what makes it, it could still be soluble, just sluggish to dissolve. And then, have you produced a rough draft of the synthesis report? I'd like to see a rough draft before you submitting the final draft. But if not, you can just submit the final draft. That's going to be due coming up soon. Okay. So anyway, I'll stop here and we'll just move over to the computer lab, and then I got to end it for today because I'll be back in the afternoon now.